Section 5.7. Index of Coincidence. The index of coincidence was invented by American cryptanalyst William F. Friedman in 1922. The idea is very simple, but its importance is profound. Imagine two messages enciphered using a polyalphabetic cipher, but with different keys and possibly with different periods. If you compare the two ciphertexts letter by letter, the chance that two corresponding letters are the same is 1 in 26, or about 0.0385. If both messages are 52 characters long, you would expect 52 over 26 equals 2 corresponding pairs of letters to be equal. Here I have enciphered the 52-letter plain text, "On the first day of spring, a young man's fancy turned to baseball," with a Bilasso cipher using the keys Mars and Venus, respectively. The two equal letters are highlighted. It is accidental that both pairs of equal letters are F. Now imagine two messages enciphered by the same key. Each pair of corresponding letters is enciphered by the same key character, so if the plain text letters are the same, then the ciphertext letters will be the same. The frequency of A is about 0.08, so the chance that both plain text letters are A is 0.08 to the power 2, or about 0.0064. The chance that they are both B is about 0.015 to the power 2 equals 0.000225, and so forth throughout the alphabet. The total for all 26 letters comes to 0.0645 to 0.0675, about 1/15th, depending on which letter frequency table you use. The chance of two corresponding ciphertext letters being equal when the same key is used is roughly 1 over 15, which is 73% higher than the 1 over 26 chance when the keys are different. This fact can be exploited to determine the key length for a polyalphabetic cipher. Let's number the characters in the ciphertext C1, C2, C3, and let the length of the key be L. We can compare the characters in the ciphertext with those same characters shifted by some number of positions, say S positions. That is, we compare C1 with C1 plus S, C2 with C2 plus S, C3 with C3 plus S, and so forth. When the shift S is a multiple of L, then CI is enciphered with the same alphabet as CI plus S for every position I, so the chance that two corresponding ciphertext characters are equal is 1 over 15. If the shift is not a multiple of L, then corresponding characters will not be enciphered with the same alphabet, and the chance that they are equal is only 1 over 26. The number of equal characters should be largest when S equals L, S equals 2L, and so forth. Trying several different shifts should make this pattern clear. The shifts producing the most matches will usually be multiples of the period. Trying many different shifts sounds like a job for a computer, but it actually can be done by hand without too much effort. Write the cryptogram onto two long strips of paper. Then just slide one strip against the other and count the number of equal characters for each shift. You need to space the letters evenly so they align correctly. This is easily managed by using graph paper or by holding a ruler next to each strip while you write the letters. The index of coincidence has another use that has proved of immense value for cryptanalysts. It can detect when two messages have been enciphered using the same key. Imagine that Emily is using a machine cipher that produces a polyalphabetic cipher with a very long period, say 100,000. For comparison, the Enigma machine used by the German army in World War II had a period of 26 times 25 times 26 equals 16,900. Suppose you have thousands of intercepted messages. Each message is enciphered using some segment of this long key. sliding each message against the others, and employing both index of coincidence and repeated ciphertext sequences, you can detect sections of different messages that have been enciphered by the same part of the key. When you have found enough of these overlapping segments of the key, you can begin splicing the segments together to get longer segments. Once enough messages are found that are enciphered with the same key segment, you can begin to solve the messages by the usual means: letter frequency, contact frequency, identifying common words, and so forth. Section 5.8. Index of coincidence, again. There is another method for estimating the period of a polyalphabetic cipher, also called the index of coincidence, and also due to William F. Friedman. This method calculates the probability that two letters are equal when there are two alphabets, three alphabets, and so on. This is calculated ahead of time and kept in a table. The idea is to calculate this same statistic for a given message and compare that number to the table. The closest match is supposed to be the period of the cipher. In practice, this often comes close, but it is frequently off by 1, 2, or even 3. When the period is more than 10, the method is useless. This method is not much better than random guessing, so it is not worthwhile to explain the details. The Belasso and Vigenère ciphers continued to be widely used through the 1880s. As the knowledge of the Kasiski method began to spread, their use diminished and they largely disappeared after the Index of Coincidence was published. Still, today it remains one of the most popular hobbyist ciphers. Several times when I told people that I was writing a book on cryptography, they would tell me that they knew an unbreakable cipher. This always turned out to be the Belasso cipher, which they would call the Vigenère. Then I had to prove it was breakable by solving a cipher they would make up. These were so badly mangled that I had to create a web page, masterssoftware.biz/vigenère.htm, to make sure that the ciphers were done correctly.